对，他们得结合录像。这边得跟他说一声。对。
Okay. Just now, Professor Zhou told me want me to host this session. I'm sorry, I didn't check the WeChat information. So first of all, thanks for Professor Guo Liu come to Shanghai ESP local conference. Okay, so I will first give a brief introduction to Professor Liu. He is currently the associate professor of the National ASIC System Engineering Research Center, Southeast University. His research interests including chip architecture design, reconfigurable computing, and many things. He has authored and co-authored more than 50 scientific papers in the above research field and hold one US patent. His research is supported by National Nature Science Foundation and National Key Research Development Program. Welcome, Professor Liu.
Thank you.
Okay. Okay. Let's share the screen.
Okay. Hello everyone. My name is Liu Bo. I'm from the Southwestern University, Nanjing. It's my honor to share our work with you. The paper I will be presenting today is titled "Efficient BCN Deployment Method Using Quality-Aware Approximate Computing." The outline for my presenting is first the motivation and the challenges of BCN deployment method, and then I will show our solutions, including 4-step optimization methods, and finally I will show you the performance evaluation of our works. Okay. As we know, CNN, which is short for convolutional neural network, is widely used in IoT device applications, such as image classification, speech recognition, speaker verification, and others. For those battery-powered devices, power consumption is one of the key requirements for hardware deployment. For the past decades, many low-power techniques has been proposed to reduce the power consumption of neural network deployment. Among such as neural network, porting, bit width quantization, network model compression, and other, and so on and so forth. Among these strategies, BCN, which is short for binary convolutional neural network, is a very useful deployment method. In the BCN, the bit width of the weight in the neural network is quantized to a single bit. This can significantly reduce the hardware power consumption and improve the hardware computing efficiency. Approximate computing techniques is very useful in BCN deployment. This method can be integrated in different parts of the hardware deployment with a consideration of the trade-off between power reduction and the accuracy loss. But there's still a question: how to deploy the approximate computing effectively in BCN This slide gives an example. This work was published on VI Symposium 2018. This work proposed a BCNN inspired speech recognition processor. In this work, the authors has proposed approximate adder to improve the hardware computing efficiency. With this proposed approximate adder, the computing hardware can achieve a PDP of a reduction of 48% with the accuracy increased by 1.27%. But there's still a question how to deploy approximate computing more effectively in BCN. So there are two, generally speaking, there are two challenges. The first challenge is hardware deployment method of approximate adder in BCN. This slide gives an example. As shown in this figure, after 3 consecutive additions, the error of traditional approximate adder can increase the MED of 10 times. The second challenge is accuracy loss becomes unacceptable as the approximate bit width increases. So efficient retraining method is required to recover accuracy for higher approximate bit width of BCN. Our solutions, we propose a hybrid addition tree structure with interconversation method. This solution includes 3 optimization methods. For the first step, we propose automatically approximated circuit design based on CGP. CGP is short for Cartesian genetic programming method. We model the circuit as a 2-dimensional array of some programmable loads. The loads are the Boolean functions for such as AND, XOR, and others. For the details of the CGP method, you can find in our paper. Based on the CGP algorithm, high performance approximate adders with customer accuracy and target distribution can be generated. For the second step, we also propose analytical model of approximate computing. Based on the analytical model, the MED of each stage of the approximate addition tree can be obtained by iteration operations. In the third step, we also propose an interconversation approach. Based on the interconversation approach, the impact of errors caused by approximate adders is significantly reduced. And this can also improve the energy efficiency of the approximate computing. Last, we also propose accuracy recovery with retraining method. Based on the network sensitivity, we have proposed a retraining approach to effectively recover the accuracy of BCN when using the approximate computing techniques. Here is a performance evaluation compared to the standard 4 adder. The approximate circuit has a rate of 32.17% reduction in power consumption and 39.44% reduction in latency. Here is the performance evaluation of the network accuracy. The accuracy can be recovered by 64.09% on minutes and 52.23% on simulcast and 66.1% on GSCD. GSCD is speech recognition application dataset. So the approximate degree in BCN deployment can rise by 50% to 75% while reducing the lateral inference accuracy less than 1%. Okay, in the last, I also prepare a video demo show for this presenting. In the video show, we have designed and fabricated a real chip for speech recognition on an industry 28 nanometer CMOS technology process. Okay, please. Okay, this fabricated real chip shows that by using our proposed approximate computing deployment method, we can not only reduce the power consumption of the chip, but can also maintain the high accuracy even on high background noise. Okay, that's for thanks for your listening. That's all.
Thank you, Liu Bo. Right, very interesting demo and work. So any questions? Probably we can take one quick question from online or in the room. Do we have any questions? Okay, probably I have a very quick question. So BCNN is binary or Boolean CNN, right? What was the?
It's a binary
CNN.
CNN, yes.
Okay.
The weight bitwise is binary, but the data bitwise is not.
It's not. Okay, understood. So where are they usually used in real applications? What kind of real applications?
Used in many AI-based AIoT devices. Okay. For example, the speech recognition.
Okay, speech recognition.
And speech verification. Many works, yeah.
Okay, I see. Could you show the performance evaluation? So who do you compare against? Your approach against what are the state of the art?
In this slide, we compare with because they have different applications and have different network features, so we compare with the others deployment method proposed by others, but the network is our design.
Okay.
So to compare with other works, we can integrate more bit with the approximate computing method.
Okay, so you can improve accuracy, or what do you improve?
We can improve the compute energy efficiency, while still reducing the accuracy loss.
I see. Okay, thank you very much.
Thank you.
Okay, so we'll move on to the second talk. Apologies in the beginning of this session. I was in the keynote speech. So the second talk, the title is Memory Computing Decoupling, a DNN Multitasking Accelerator with Adaptive Data Arrangement. The speaker is Chuxi Li, a PhD candidate in the School of Computer Science, Northwestern Polytechnical University. She received ME in Northwestern Polytechnical University. Her main research interests include computer architecture, machine learning, and neuromorphic architecture. Chuxi, please.
Good afternoon, everyone. I'm Xiaoti from Northwestern Polytechnical University. The scheduled speaker, Li Chuxi, is unable to present in person because of the COVID-19 policy, but she will communicate online with us. Anyway, I appreciate the opportunity to attend this conference. The topic of the paper is Memory Computing Decoupling, a DNN Multitasking Accelerator with Adaptive Data Arrangement. Multiple networks are increasingly used in real-world intelligent applications on edge. In these applications, multi-DNNs work together to complete different tasks. The network layers are heterogeneous in shape and scale. Thus, they prefer distinct data flow patterns when deployed on a prevailing hardware accelerator. And their features and weights can be partially shared. As an example, although the two layers share the same input tensor, the difference in data flow makes the order of data index and assigned very different. On the DNN accelerators that enable multiple data flows, we detect a dimension mismatch between parallel processing and the linear memory arrangement. Firstly, the bus through which the data is loaded and stored from the off-chip memory is burst-based. The data in a burst has one-dimensional continuous addresses. However, the subtensor indexed by the computing unit in each cycle are scattered in the memory with discontinuous addresses. Thus, the high probability outcome is that the data needed immediately take more burst loads to move from the memory to the processing unit. On the other hand, the tensor subset are cached in the on-chip buffer and then distributed to the processing unit. Inferior arrangement may cause bank conflict so that the needed data is congested in the thin bank, which traps the on-chip bound ones into wasting time for fetching data. Therefore, in this week, we decoupled the storage and computation for multiple tasking DN accelerators. As shown, these three design considerations and challenges are discussed. Firstly, we defined the two paradigms that describe the divergence degree for off-chip and on-chip tensor access of DN models. In fears that the dispersion of tensor data in memory leads to an overall decline in performance and throughput. Inspired by the tensor dimension mismatch, the data arrangement framework includes obtaining the mapping relationships, dividing the tensor into small blocks, assigning and distributing the blocks. We begin by identifying a block as a collection of tensor elements to be the scheduling objective. Blocks is designed to have two features, compactive and effective. Compact means that a block is stored in the off-chip memory in consecutive addresses. Effective means that all the elements contained in a block are effective for at least one circle. The block division is performed in the data collection stage. First of all, the time-space stamps and the data assignment relationship are extracted from data flow relationship. Thus, the patches are built. A patch is a high-dimensional subset contains elements that are operated in one cycle by the processing unit. The dimension and the size of the block are determined by the maximum non-overlapping subset of the temporal adjacent batches. Thus, the elements in a block are tilted on a region of the B array, and the elements inside the block are not temporarily reused. When two or more tasks are shared features, the patches for these layers should be built separately. In this case, the blocks are determined at the intersection of the subset of the parallel line layers. In the data preparation stage, the divided blocks are loaded from the off-chip memory to the on-chip buffers through a serial transmission interface to avoid bank conflict as much as possible on the premise of ensuring the spatial reuse. In our block assignment, the blocks are interleaved into the on-chip buffer according to the index order of the spatial stamps. In this way, in the distribution stage, a direct mapping between the data provided by the 1 million dimensional addresses and the data consumption by parallel high dimension computing established. We handle loading, assignment, and distribution of blocks at the near input end. The input blocks are loaded serial from the off-chip via successive bursts and cached in the buffer banks through the serial to parallel conversion circuit and the multiplexer. In every full cycle, the full divided and arranged blocks from a single patches are fetched to the serials to parallel circuit and are written into the on-chip buffer.
2 more minutes. 2 more minutes.
Okay. We complete the block diversion at the near output end. Following computing, each obtained elements is reordered in the output buffer through the multiplexer and grouped into specific blocks. To demonstrate the efforts of correcting the dimensional mismatch, we first use the two network layers as a test case. It's showing that compared to the baseline without considering data arrangement, the proposed method shows a higher energy efficiency. We evaluate three types of the multitasking applications workloads on our architecture and the state-of-the-art multitasking accelerator called HDA, as well as three fixed single digit load style accelerators. It is shown that our design with data arrangement achieves both energy efficiency and throughput improvement compared to the baseline. We also compare the system area and power consumption with memory. By avoiding the adoption of large-scale trace switch array, we achieve an 8.3% area overhead and a 4.7% power saving. Okay, this concludes my presentation. Thanks for your attention.
Thank you. Thank you. Thank you for the presentation. So any questions from online? From on-site? I think the performance improvement is very impressive, right? 30% in energy efficiency and 60% in throughput. So any questions from the audience? So what's the main method? Can you summarize it? So you're doing memory computing decoupling, meaning you are using less of the on-chip memory, but off-chip memory, is it? Or what is the main message of your method?
Xuetao is online now.
Okay, maybe she can answer.
Yes,
yeah.
she will answer.
Yeah, just unmute yourself and speak.
I'm sorry. Can you repeat your problem? Your question.
So because so based on what I see, right, what I saw in the presentation, the performance improvement is significant, like 30% compared against SOTA, 30% improvement in energy efficiency and 60% in throughput. So what is the main message? So how did you mainly achieve this? So you're doing memory computing decoupling. Is it you are using less of on-chip memory, but more of off-chip memory, or what is the main method? Can you summarize?
Oh, we save the cycles on fetching data from the off-chip memory.
Okay. And how did you exactly do it?
Okay, let me explain these questions by Xiaoti. Can you change the slides to a previous one? Previous. Okay. Please look at this picture.
Could you explain? Could you say something?
Okay. Wait a minute. In the accelerators, the dimension of the tensor data in the memory system and the computing units are different, so it takes a lot of unnecessary times to fetching the data from the memory bank.
To access the memory bank, yeah, understood, yeah.
Yes.
And then,
so our keynote is to collect the tensor elements that required by the processing units in the same time to continuous tensor subsets and to fetching them into the same burst. In this way, we can save the burst times to fetching data from the upstream memory. That's our key idea to improve the throughput and the performance.
Okay, understood. Then why do you call that decoupling?
It's a good question. Because we
anyway, I think yeah, please.
Any questions else?
Okay. Yeah. Anyway, I think we got the main message. Okay. Thank you very much for the presentation. Yeah.
Thank you.
All right. So yeah, we'll move on to the third talk, the third paper. By the way, this is Wang Li, the session chair. Neural map, efficient task mapping of deep neural networks for dynamic thermal management in high bandwidth memory. The speaker is Shaya Pandey. I hope the pronunciation is correct. Pandey is a PhD student in the Department of Computer Science and Engineering at the Indian Institute of Technology, Delhi, India. She obtained her master's degree in computer science and engineering from the IIT Kharagpur, India in 2016. Her research interests include performance optimizations and thermal management in novel memory technologies. Please.
Yeah, hi everyone. Is my screen visible?
Share screen. Switch.
Yeah, we switch to the presenter screen. Otherwise, it's Muhammad.
Yeah, should I start?
Just a second. Yeah. Excellent. Yeah, we can hear you and we can see your slides. Yes, please.
Okay, great. Yeah. Okay, I'll start. Hi everyone, I'm Shelza. I'll present our work titled NeuroMap, Efficient Task Mapping of Deep Neural Networks for Dynamic Thermal Management in High Bandwidth Memory. Emerging memory technologies such as 3D stacked DRAMs provide bandwidth as high as 386 gigabytes per second. HBM is used in GPUs and AI processors to significantly accelerate modern data-hungry applications. A 3D DRAM is composed of multiple DRAM dies vertically stacked together, each die comprising two independent channels. HBM consists of a lower stack 0 and an upper stack 1. A channel in HBM consists of portion of DRAM dies from both lower and upper stack. The vertical integration results in high power density, causing poor heat dissipation capabilities and associated thermal challenges. 3D DRAMs exhibit significant thermal gradient across DRAM dies. Assuming a heat sink at the top of the stack, bottom channels are hotter than the top channels. Systems running under thermal constraints often employ dynamic thermal management policies to keep the memory channels within safe thermal limits. Consider a multi-core processor system and an off-chip 3D DRAM, such that a subset of cores is mapped to HBM channels, that is, the requests originating from cores are serviced through the specific channel. When a channel gets heated due to aggressive memory requests issued at cores, the corresponding cores get stalled. Since the emergence of 3D integration technologies, thermal issues in core and memory has become a first-order concern. Prior works on dynamic thermal management in 3D DRAM do not consider application knowledge while making DTM decisions. In this work, we make a case for harnessing application awareness in order to reduce the associated DTM overheads. We focus on deep neural networks. Okay. Deep neural networks such as CNN consist of a series of alternating convolution and pooling layers, followed by fully connected layers towards the end. DNNs execute in phases and exhibit varying memory access behavior in different layers. The memory access rate, which is primarily responsible for heating in the HBM, shows a high correlation with the data access volume and the data reuse policy that is used across the layers. The left graph here shows the variation in the memory access rate across layers for AlexNet neural network. The initial convolution layer exhibit highest access rate, followed by the fully connected layers towards the end, and then the intermediate convolution layer. Likewise, the right graph shows the variation in memory access rate for different reuse policies, which is wait, output, and input reuse. Different layers exhibit varying thermal impact depending on the memory access intensity of the layers and the physical location of channel. As we can see, with the layer transition, the peak temperature of the memory varies significantly. We propose an efficient task mapping based dynamic thermal management policy, which minimizes the execution time of DNN workloads and keep all the memory channels within safe thermal limit. We focus on reducing the number of thermal stalls and the duration of each such stalls, because the execution time primarily depends on these two parameters. Our neuromap policy consists of a series of optimizations, which we talk about in the next slides. We first categorize the cores into 3 core groups, heavy, medium, and light, such that heavy cores map to the top channels, medium to the middle, and light to the bottommost channel. In this way, we leverage the thermal gradient across DRAM dies and avoid vertically adjacent thermal hotspots. Next, we illustrate the task to core mapping performed by neuromap. We identify a DNN layer as a task and categorize the DNN layers based on memory intensity as light, medium, and heavy tasks. A light task first searches for an ideal core in the heavy group. Upon failure, goes to the medium group, and again upon failure goes to the light group. Similarly, the medium task begins the search in the heavy group and continues in the medium group. And finally, the heavy task searches in the heavy core group. Assuming a task assignment at time t1 as shown, when an application core transitions from a light phase to a heavy phase, it is migrated from the light group to the heavy group. Whenever task mapping and migration is not feasible, neuromap performs application swapping amongst the cores. Assuming the task assignment at time t1 as shown, and application 9 transitions from a light phase to a heavy phase at time t2, neuromap sees that there are no free cores in the heavy group, and thus it swaps application 2 and application 9. Finally, when assuming the assignment at time t1 as shown, when application 13 transitions from medium phase to the heavy phase, however, there are no free cores in the heavy group and also no potential swap candidate. In such a scenario, neuromap continues running the application in the same group, however, with a reduced core frequency. Finally, we talk about the low-powered state-based DTM policy that is implemented on the memory side. The memory starts at the initial state. Once one or more channels get heated, the memory transitions to the heated state, where the heated channels are put to standby mode. Upon recovery of heated channels, memory goes to the active state, and upon heating again, it goes back to the heated state. We discuss the baseline task mapping policies against which we compare the performance of neuromap. The policies are first unused, random, and round robin. In our experimental infrastructure, we use COMET Performance Thermal Simulator, which consists of integrated toolchain comprising Sniper, Hotspot, Cacti 3DD, and MacPad. We have significantly contributed towards the development of COMET simulator. The top table shows our simulated architecture, and the bottom table shows the workloads used. We use 7 popular DNNs with diverse characteristics and create 5 workload mixes. The left graph shows the execution time comparison of different baseline policies. NeuroMap is able to perform 7 to 39% reduction in the execution time and 12 to 40% reduction in the memory energy, primarily by reducing the number of thermal stalls and the cooldown period of heated channels. We compare the thermal stalls that are incurred across different baseline policies and NeuroMap. As can be seen, NeuroMap incurs minimum number of stalls by proactively managing the channel temperature through efficient task mapping and prevents the channels from skipping the T-critical limit. As can be seen, the execution time with NeuroMap is minimum. We quantify the impact of individual optimizations that makes the NeuroMap policy. Enabling only low-powered state mechanism provides only limited bandwidth. Low-powered state plus task mapping provides benefit. However, it performs poorly, like for workload 2, where no swap candidate is available at some point in execution. Low-powered state plus DVFS mechanism performs poorly for workload mixes like workload 4, which has short-lived apps in the mix. Finally, NeuroMap performs best across all workloads, and the performance comes from the interplay between the optimizations when all of them are enabled together. We talk about the implementation details. The task mapping and migration policies are implemented in software. We model the overheads in the simulation. The DRAM low-power state-based DTM is also implemented in software and periodically sends the power state of ranks and channels to the memory controller. To conclude, we propose an application-aware DTM policy for running DNN inference, which uses efficient task mapping to minimize the associated DTM penalty. We plan to release the implementation of NeuroMap to the COMET simulator, including the integration of task mapping and DTM policies and integration of DNN benchmarks. In the future, we plan to explore data mapping alongside task mapping, incorporate variable refresh rate, and experiment with higher HBM stacks. Thank you.
Thank you. Thank you for the presentation. So any questions from the audience? So there is a question. Just a second. Let me see.
Yeah, I see the question. What special aspects, characteristics of DNNs were considered when designing your application-specific mapping, migration, swapping policies? Are these policies not optimal for generic workloads? Okay, that's a good question. So basically, we did observe that as the layer transitions in deep neural networks, their memory access rate varies vastly. And it also varies with the data reuse policy that is being used within a layer, which is determined by the loop scheduling scheme of the convolution operation. So we did leverage this change in the memory access rate across layers in our DTM policy. The second question is, are these policies not optimal for generic workloads? Well, we did use neural networks in our setup. However, if we are able to dynamically gather the variation in the memory access rate of generic workloads, the policy will work well. Just one thing is that dynamically collecting this information of variation in the memory access rate would require reading the performance counters, and which may be a significant overhead if not handled properly. Does that answer the question? Sorry, what?
Yeah, Mohammed raised his hand. Mohammed, please.
Okay.
Okay.
Thank you very much, Shailja. Can you hear me, Shailja?
Yes, I can hear you.
Okay. So thank you very much for the presentation. I have a very general question. So you are assuming that the CNN is parallelizable, or you are just taking, because it's a very sequential architecture, am I right? The task model is extremely sequential, and you are taking SOC,
Right.
heterogeneous and three-dimensional SOC. Is it just you assume that it can be parallelized, or there is evidence?
Okay.
Okay.
Yeah. So I did show in the slide the sequential architecture for a deep neural network. However, in our workloads, we did experiment with recurrent neural networks, which have feedback loops. So yeah, the policy does account for the feedback loops in the neural network architecture and performs well.
So you gained also latency gain. Did you gain basically by parallelizing into multiple cores, basically? Did you check?
No, okay. So,
latency?
yeah. So as far as execution time is concerned, we did not parallelize at the application layer. So we run single-threaded inference. However, the policy should be extendable for multi-threaded inference as well, where a single application is running across multiple cores based on the parallelism available in the application. However, that is an ongoing effort.
You haven't done it. Okay. Thank you very much.
Right. Okay.
Thank you. Any more questions from the audience? So probably I have a very quick question. So what are the thermal models used in this work?
Okay. So the thermal models, we use hotspot thermal simulator for modeling the temperature. And we assume the placement of temperature sensors, 2 sensors per die in the 3D DRAM stack. Yeah.
And you consider DVFS?
We do consider DVFS.
Is there a choice? How is DVFS integrated in this work? So how do you consider that? Is it the option to make a...
Right. So the neuromap goes for DVFS only when there is no feasibility for migration or swapping, because running a heavy task on the bottom cores has significant impact on the HBM channels, because we use static core to channel mapping, right? So we go to DVFS because we see limited performance gain with DVFS. So that is our last mechanism that we prefer. We go in a particular order, and when swapping is not feasible, we go for DVFS, because we don't want to stall the application altogether because of unavailability of a preferred core. So we run it with a lower frequency.
Okay, understood. Thank you very much. Maybe another question, right? Just very quick one. So in the performance evaluation, just out of curiosity, so you're comparing against a number of algorithms, but
right.
They are quite basic algorithms. But task mapping is a well-investigated topic, but probably not for DNN and this dynamic thermal management. So is there any existing task mapping method that can be used over here? Compare against? Could you make some comments on this?
Sure. So if you see our baselines, we use 5 baselines. One of them is FastCool, which is state-of-the-art for thermal management in 3D DRAMs. However, the FastCool policy performs data migration to the backup 2D DRAMs, and therefore it's a very high penalty for DNN-like workloads, which show aggressive memory accesses throughout their execution, right? So FastCool is one state-of-the-art baseline that we can compare against. Next, baselines are the classical task mapping policies. However, they are derived from the best possible task mapping that can be done. For example, round robin is one of the best approach to actually balance out the thermal impact across HBM channels. So if you see that for workload 2, round robin is very close to neuromap, because it depends on the mixes that are used in the workload, right? So when the mixes are similar, round robin is as good as neuromap. However, when the mixes are different, when they are diverse, then round robin, which is considered to be best task mapping policies, we see performance improvement with neuromap.
All right, thank you very much. Very
Okay,
clear
thank you.
presentation and yeah, question answering. Well done. So we'll move on to the fourth talk. The paper title is on transferring application mapping knowledge between differing MPSOC architectures. So the speaker is Yan Speak. Yan received a Bachelor of Science degree with distinction and a Master of Science degree also with distinction in computer science from the FAU Erlangen, Germany, 2016 and 2019 respectively. So at the same place, he is pursuing the PhD degree under the supervision of Professor Yungen Taish. In 2019, he joined the chair for hardware software co-design as a research assistant. His current research interests include hybrid application mapping for many core architectures with a focus on scenario-aware and machine learning-based techniques. Yan, please.
Okay, can you hear me?
Yes, we can hear you and also see the slides. Yes.
Okay, perfect. Yeah, thank you for the nice introduction. Then let's start. So if we want to look at the mapping of an application given as an application graph to a heterogeneous MPSOC architecture, shown here, then normally we perform a design space exploration to gain some Pareto front regarding some objectives like energy consumption or execution time. And each of these operating points is then a special mapping of the tasks to the hardware resources. The disadvantage of these is that the resulting mappings that we gain here correspond to a specific fixed architecture that we have as an input. But changes to the target architecture can happen due to many reasons. For example, hardware upgrades, which means that the source architecture is given here and our new target architecture has a higher complexity. The same can happen inversely. That means hardware downgrades from a more complex architecture to a lower complex architecture, or some resources fail and we have to change them. Or the last point would be architectural degradation, which means that after some time, let's say after 10 years, our architecture does not reach the maximum frequencies anymore. So we have aging effects and the maximum frequencies are changed. And our goal is now to transfer the mappings to the changed target architectures without having to perform the complete reoptimization by the design space exploration, which can days to weeks for complex optimization problems. And our proposed approach has a fast approximate transfer, which only takes seconds compared to days and weeks. And then because our approximate transfer is approximate, we also have a refinement phase where we can build on these founding mappings here and make them even better. And this is done then in hours compared to days and weeks. So how does this look like? So this is our flow. This is what happened already. We have a given application at architecture A. We performed mapping optimization and have gained some mappings for the old architecture. But now a new architecture arises, so that is Arch B here. And now we perform our greedy transfer heuristic to gain a new set of mappings that are feasible for the new architecture. This is built on the mantra that we want to extract as much architectural and variant knowledge from previous optimizations. And we want to make this fast, but imprecise, and then improve on that with the refinement later on. And we use mapping intuitions for that. So mapping intuitions, how do they look like? We have 5 presented here. There are more on the paper, but I want to limit myself in this presentation. So one idea is to maintain task groups. That means if multiple tasks are mapped to the same resource on the original mapping, then we want to maintain that for the new mapping. B would be maintain resource characteristics. That's so we see, okay, we have mapped it to this special resource in our original mapping. Let's keep it similar to keep the mapping with similar characteristics in the end. Then prioritize unoccupied resources. That means if tasks are already mapped to a resource, then for a new task, choose another one. Then prioritize tasks by computing needs. That means map tasks first that have high computing needs, so they have more options where to map them. And the last one would be map communicating tasks close to each other, which reduces then the communication times. So a quick example. So we have our original mapping here, and we have an architecture A1 where we want to map it now, and want to gain a new mapping MA1. So let's see. So first we apply ABD. That means we look at our computing needs and see, okay, tau 0 has the highest computing needs, so let's start with it. And then we also see tau 0 is mapped together with tau 2. So let's map them together to a new resource. And for that, we also use intuition B, that means maintain resource characteristics. So I have color-coded the resources, so they're heterogeneous, and orange here means that it's pretty similar. So that's why we map tau 0 and tau 2 to the same resources up here. Now only one task is left, which is tau 1, and where to map it. Now, for this, we can also look at our intuitions. In this very easy case, it's more complex, of course, in real examples. And here we see we want to maintain resource characteristics. It's also mapped to an orange resource, so that would be this here. And we can also see we want to map it close to each other, so this would be also suitable. So in this case, we don't have any conflicting intuitions, but if we have conflicting intuitions, then we have an order in which we prioritize our mapping intuitions, and that can be seen in the paper. Okay. So now we have gained some initial mappings on a new architecture, MB, and we want to refine them. And for that, we have this proposed refinement process where we have 3 parts. One is latency optimization, one is energy optimization, one is trade-off optimization. Because of timing reasons, I won't go into details here and only look at the general refinement process, which is displayed here. So we use our greedily explored mappings MB as a baseline, and our principle is that because of the simplifying assumptions of our greedy heuristics, partially suboptimal mappings are gathered in the greedily explored mappings. And we want to keep the general structure of these mappings during refinement, but improve on a task granularity. That means we look at one task at a time. And for that, we have our mappings here, and then we want to choose a mapping to improve. This can be done by multiple things. For example, we measure the hypervolume. In this version, we use a very easy solution. We just pick members randomly to improve. Then we have a selection agent, and the selection agent then chooses a task that we want to remap to a new resource. And this task is selected based on some criteria that the selection agent learns. That means the selection agent chooses a task to remap. Then we see, has the remapping of the task any positive impact? If yes, then we have a positive reward for the selection agent, which is based on reinforcement learning. And if not, then the task remapping wasn't that good, and that means we don't have a high reward, and the selection agent will probably choose another task later on. And with that, we get better results than just randomly selecting tasks to remap. Finally, we have the refinement heuristic. And heuristic is maybe the wrong word because it's based on both heuristics and real measurements. And we can tune our ratios. We can choose, okay, we want to really measure how the remapping of the task impacted the qualities of the mapping regarding, for example, energy consumption or latency. Or the second point is we can use our heuristic that I also present in the paper to speed that up. And with that, we can have the best of both worlds. So we can have real measurement and heuristics and have a fast refinement process. So we don't have to measure the mapping each iteration. And with that, we gather then our final set of mappings that are shown here to the new architecture RGB. Okay, let's evaluate it. We have multiple applications with different tasks, and we use multiple architectures for testing where we want to transform between them. And we have 6 different core types, different caches, different interconnect structure, and so on. And we simulate it all in our heterogeneous MPSOC simulator. So this is the results. We showed a hypervolume upon convergence, and that it's normalized. It means 1 is the best. The compared approaches are honoring, which is the state-of-the-art heuristic. Then we have our proposed greedy transfer heuristic, then proposed which should be greedy plus our refinement. And then we have a state-of-the-art DSE. And the transfers shown here are upgrades from 3 to 4 and 4 to 8. That means 3 times 3 tile architecture and 4 times 4 tile architecture, 8 times 8 tile architecture, a downgrade, and also some degradation where some of the maximum frequencies can't reach anymore because the architecture has aged for 10 years. And the results for the hypervolume are shown here. And we see that we are better than our baseline honoring state-of-the-art heuristic with our greedy transfer heuristic in all cases, and mostly significantly. And then with our proposed refinement, we also see that we have always small improvements, sometimes even big improvements between our first state, our greedily suboptimal state, and then the final solution. We come very close to the DSE in most cases, but the DSE is better for some applications, but also takes significantly longer in the optimization time. So then also look at the hypervolume at epsilon dominance development that can be seen here. So epsilon dominance lower is better. That means 0 would be the best. Hypervolume higher is better. So 1 would be the best. Both is normalized. And we can see that our blue line, so we are blue and orange would be our DSE approach. So the blue reaches a far lower epsilon dominance and far higher hypervolume from the start because of our greedy transfer heuristic, and then improves it also over time. And in the first couple of thousand iterations, we are always better than the DSE for this setup. And just to give you some numbers, the optimization time for the stitching applications to reach more than 96% of the final hypervolume, we only need 5 hours for proposed and 70 hours for the DSE approach. Okay, to summarize, so I've presented a novel mapping optimization methodology for heterogeneous episode architectures. We want to extract architecture invariant mapping knowledge from previous optimizations. Then we have 2 approaches. One is a fast greedy transfer for immediate mapping adaptations, then a refinement heuristic for improving the mappings even more based on a threefold optimization scheme. And we can consistently accelerate the mapping optimization compared to state of the art. So what is the future work? At the moment, we are only looking at tile-based architectures. So that means we want to apply the principle also to other architecture types. Then we only look at the design time aspect of transferring the mappings. But if we have some hybrid application mapping scheme, that would also mean that we have to adapt our runtime manager based on the architectural changes. And with that, we can then finally have, this is future work, a complete transfer process for hybrid application mapping. Okay, thanks for listening. Are there any questions?
Thank you for the presentation. Any questions? Any questions from the audience, please? If not, because we are running a little bit late, so we'll wrap up this session. So in this session, we have heard 4 very interesting talks on 4 papers. So the first 2 on neural networks, one using approximate computing, the other considering the memory access, and then also 2 other works on task mapping. So if there is no further question for any of the papers, then I'm going to wrap up this session. And thank you very much for attending. Thank you.